Hello everyone, my name is Sunil and we are discussing as a part of this series is some EVPN concepts, and this is our third session on EVPN. I'm sorry, fourth session on EVPN, where in the previous three sessions what we have covered is like first why you need to learn EVPN, and we have talked about the need for EVPN in the data center network. We have talked about some SP case studies where EVPN is deployed. We have also looked at some enterprise use cases as well, where customers are considering EVPN. And this is even evident from the vendor side as well. If you take some of the vendors like Cisco, Juniper, they support EVPN gear in their enterprises segment devices, SP, or even in the data center side as well. And believe me, if there is a vendor who is investing in these, that means there is a market demand for that. And what I'm trying to say with this first point is that irrespective of your networking domain, whether you are working in data center, working in service provider segment, or you are currently handling enterprise network, you should invest some time and learn EVPN, right? So this is what we have covered in our first session. Then in the second session, we have talked about some of the key fundamental differences, some of the key problems that were there with the legacy networks, let's say VPLS or other type of layer 2 networks, and how EVPN have solved it. So we have basically covered the big why behind a new technology which is EVPN, and in my opinion it is utmost important for someone to understand the reasons like why EVPN came into picture in the first place and why it had become so popular that data center SP enterprises have started asking for it, as I was saying like just few minutes back. So we have talked about that fundamental issue and how EVPN have solved that. And then in the third session, we have talked about some of the basics that or some of the thoughts that had gone into EVPN. Why these concepts of multi-tenancy came into picture, the benefits of virtualization, which was so far limited to the server side or the storage side, when this networking industry thought that virtualization benefits, and by the way there were tremendous benefits that we had seen on the server and storage side of it, they wanted to bring that all to the network side as well. And when the networks got virtualized, what is the role that EVPN has to play into that? And why, in the first place, BGP along with EVPN came into picture? So, this is what we have discussed in our session 3. So, the point that I'm trying to make here is that with session 1, 2, or 3, it is approximately 2.5 hours of content, and I'm just talking about the why layer there. I have not touched much on what EVPN is, what are the route types. I had only shared some reasons like why the industry is looking for it and why you need to invest some time into this. So go ahead and watch if you haven't seen those sessions. That would be my request, because this session also we will be connecting some of the dots which we have covered in previous three sessions. But since this is our fourth session, we are talking about EVPN finally. That's what we will be touching basically in this video, route type 2. But before that, we will also look at the VXLan, basically the building blocks, the encapsulation that has been used in the EVPN. Mostly if we look at the data center and even if we look at the campus side of the solution, uh, and I'm talking about Cisco side. And then we will cover a packet walk in an Ethernet VPN network. And I will show you how, with some animation, the VXLAN packets get added to our original layer 2 packet. So the whole sole purpose of EVPN, why we are even discussing about it, is to connect some disjoint L2 network. Let's say you have a L2 network here, you have L2 network here. Somewhere you have this layer 3 network, and you want these two networks to talk to each other. This is the key purpose for EVPN, right? And since we are talking about layer 2 here, so what is that one thing that comes to your mind when you think about layer 2? It is switching, right? Whenever we say that, okay, this is a layer 2 network, we normally deploy a bunch of switches, connect the endpoints, maybe configure some VLANs onto it. So I have taken the freedom to talk about some of the L2 jargons as well, and why this L layer 2 was there, or do we still need layer 2 networks? Now we are still carrying this, but is there still a need in 2023 that we should extend our layer 2 networks? So I will cover some of the thoughts around that into this, though not directly related to EVPN, but just to give you some thoughts, provoking session, and spark some thoughts in your mind as well. So we will be talking about this as well. But before we get into the agenda or into the points that I have discussed, let me share some building blocks. Let's say if you want to put some blocks and divide this EVPN into multiple technologies, like what are those basic building blocks that you should be aware of, then this is how you will divide it, basically, that we will be talking about now in the next 5 minutes or so. So as I was saying, EVPN connect the layer 2 network, right? I just told a few minutes back. So when it connects to layer 2, that means we have discussed that the switching comes into the picture, right? So you need to understand, if you want to understand the EVPN, some of the switching fundamentals basically. And more than switching fundamentals, I would say, what are those inherent problems that we have talked in session 1, 2, and 3? You need to understand those to set a strong foundation for EVPN. And believe me, when we talk to candidates who come and write out their CV that they know EVPN, and when we just go into some thought provoking sessions, we see them lacking on some of the fundamental aspects. So please invest some time in learning switching fundamentals. Though I'm not covering those in details, but I had made sure that at least you understand the problems, the reasons why, and what EVPN is solving for us. Right. Then the next thing, as I was saying, right, the virtualization benefits, those were clear on the server side, on the storage side. So why not bring that onto the network side as well, right? So the virtualization, how it is implemented, where it is originated. Again, I'm referring back because these sessions are interdependent on each other, and that's why we are recording this as a series. So we have talked about network virtualization in the previous section, and then as the fundamental need to carry this layer 2 networks or connect these layer 2 networks which are spread across in multiple locations, let's say, or at a distance, right? They are not directly connected. We are using EVPN. I'm reiterating this point again and again, and we'll do it one or two times more in the upcoming slide. But so that just to make sure that you get the point. But irrespective of EVPN, irrespective of VXLan, irrespective of all these advancements that we are talking, the fundamental behavior of Ethernet should not be changed. That's how the Ethernet is designed. It is something that learns by flooding. If I don't know who is Ravi in the room, I will go ahead and shout in the room, "Hey Ravi, listen to me." That's how everybody will listen. That okay, I'm asking for one gentleman, but only Mr. Ravi will respond or will raise his hand. That's how Ethernet works. And for that, if we want to cater that in EVPN, we need to understand a basics of up to some extent the multicast as well. There are multiple ways, like there is an ingress replication as well, but this is also one of the fundamental building block of EVPN. Then we, as a network engineer, if you are somebody who is a experienced person, though I am keeping this session at a very fundamental level so that even the beginners can understand, but there will be few thoughts here and there which even the experienced user will be able to reconnect, right? So whenever we see anything like any problem or something and we want to get around it, in networking one of the famous thing that was done over a period of time was encapsulation. My first encounter with encapsulation was happened with GRE, generic routing encapsulation. Then we came up with IPsec. Then I was got an opportunity to work with MPLS as well. And believe me, even MPLS is also some sort of encapsulation. Then you have some vendor specific stuffs, right? The OTV. And finally, if we are following this series, want to learn EVPN, you need to learn another encapsulation which is called VXLan. So here I am writing any encapsulation because EVPN can work with MPLS as a data plane or VXLAN as a data plane. So these are the two which I had seen mostly deployed in the data center and service provider network. In enterprise, also I had seen that it used VXLAN, right? And then finally, we need something in the control plane also. I don't want to go into a class and shout that who is Mr. Ravi. whereas I just can go to a watchman who is sitting at the gate of that class and ask, Mr. Watchman, is Ravi is there inside? He will look at his register and tell me that, okay, yes, Ravi is there inside or Ravi is not there inside. And if you are not able to relate to this analogy, don't worry, we will cover that in our upcoming slides. So, but that control piece here is BGP. So, multicast encapsulation BGP, when you mix up all this, when you mix up these ingredients, right, the recipe that come out of it is the final product that come out of it is BGP EVPN, right? So all these you need to understand. I have tried my level best and still doing to explain you this, and we have done this in the previous lectures that were recorded and in the upcoming few lectures as well, that we will focus our discussions around these things. Okay. So with that, now let's come and scratch the surface of VXLan. What VXLan is. Now I have touched this in the previous videos, but here let's just look from the introduction perspective. And again, I'm reiterating this point that EVPN's main function is to support layer 2 networks. Right? You have one layer 2 network here, one layer 2 network here, and in between you have this layer 3 network. You want these two below network to talk to each other. You need some sort of overlay. You need some sort of tunnel that can talk to, that can help basically in communicating between these two networks. So that is what the VXLAN do, right? We will look at the packet structure of it, and I think it will be cleared after that what I'm trying to say now. But from the definition perspective, if somebody asks you, VXLAN is nothing but a MAC address, right? When we say about MAC address, means we are talking about a layer 2 packet, right? So this layer 2 packet is encapsulated into a IP UDP. Why UDP? I think by now you should be able to answer, right? If not, just give me a few minutes. So you take a layer 2, we call them as frame. Packet is something that we call at layer 3 basically. So L2 frame, you encapsulate it completely into a new IP packet. That is what your VXLAN packet is. It is all IP, unlike MPLS, which is nothing but just a label. So, and then as I was saying, because this is a IP/UDP encapsulation, it is allowed to be extended across the layer 3 network. Here is a layer 2 network, L3 network, and then you have your same L2 network here. Basically, they can talk to each other if they are connected like this, right? Why we need to do this is again, I would say Go ahead and watch the previous three lectures. There it is covered in much more details. So we are talking about this VXLan for last few minutes. Let's just look at how does a packet format looks like. So this is the picture which I have taken from some of the Cisco document. There are so many fields into this, but don't worry. Let's just talk about it one by one. So this is your original Ethernet frame that come from the end host. Your end host is sending this layer 2 frame. So this is your end host, let's say endpoint. It's connected to a switch. This switch, we call it as VTEP. I will cover the definition of VTEP in the upcoming slide, but just think that this is a VTEP. What this VTEP will do is, it will put this encapsulation, that purple one that you see into this, right? And in that encapsulation, basically a packet come, I will wrap it, I will gift wrap it into this VXLan IP packet, right? So now, what are the fields in that? Right? So the first thing that comes here is this VXLan header, right? And if we open this VXLan header, you will see most of the bits are reserved here. Why reserved? In the networking, and even if we will see this in our Ethernet thought-provoking slide as well, that I will be there, I think, after 2 or 3 slides, that backward compatibility is very much important. Now I am not going into the depth of OTV and other encapsulations that were there before VXLan, and they were used to achieve the similar purpose. These reserved bits were more or less kept for those the backward compatibility. But this is not a comparison into OTV or VXLan and how OTV, some of the thoughts were taken into VXLan by its inventors. I'm not going there. The only thing that you need to look or watch out in this header is this VNI. What is this VNI? Why you need it? Right? This is the most common question that I get sometimes, that okay, we are confused with this VNI. There is a layer 2 VNI, there is a layer 3 VNI. Now, I will be talking about VNI in the next slide. So hopefully this concept will be clear by then. So for now, hold your thoughts if you don't understand what VNI is. Then, if you recall from session 3, we have talked about one of the key fundamental issue with encapsulation. In fact, it was one of the big issue with MPLS as well. From those of you who are from the MPLS background watching this, there was the problem of this load balancing, right? Take a step back and see how a router or a switch load balance the packet. It do this based on the source IP, destination IP, port information, blah blah blah, right? But if I'm encapsulating it, right, this address will be of this VTEP. That means there is this endpoint 1, there can be another endpoint here, even though different IP address, but it will get encapsulated into same VTEP IP address. That means the node after this will not load balance. So since we had seen this problem with GRE, we had seen this problem with MPLS, and in MPLS there were some hacks that were used like entropy labels and all. I'm not going into that complexity for now. But VXLan, the people who were designing VXLan, they knew this point beforehand. And what they have done is they have came up with this UDP header where the destination port was known that okay, for the VXLAN they need to use certain fixed port number, right? That destination port number was fixed, some 4000 something, right? But the source port was something that these inventors could play with. So what they told is that okay, this UDP header we are putting because we want to load balance, and the source port will be dynamically calculated based on the hashing of the endpoint. So if a packet is coming from endpoint 1, this UDP source could be, let's say, some value 100. If the packet is coming from endpoint 2, this could be 101. So that way, when the intermediate node, they see that, okay, there is some difference between the packet, so let me just load balance. That's how the load balancing was solved. And that is the reason, my friends, UDP was included. Okay. Then come to the IP. That is nothing but just your IP addresses, source IP, destination IP. What is the source IP? Ingress VTEP. What is the destination IP? Egress VTEP. Okay. And rest all are these MAC headers. We will look at these in some of the upcoming slide. But the key fields, the VNI, VXLAN, UDP header, and then the VTEP source IP and destination IP is what you need to understand if you want to understand the VXLAN fundamentals, right? So now let's just talk about this VXLAN tunnel endpoint. I bet you learn VXLAN and not hear the term VTEP. It is virtually impossible not to hear VTEPs, right? So VTEPs are basically the VXLAN tunnel endpoints, as I was showing here, right? I can have this endpoint segment here, which have, let's say, multiple endpoints, right? So this segment can be connected or can be mapped to a VXLAN segment. What is this VXLAN segment? Nothing but just a VNI. And I will tell you what VNI is. Right. But VTEP, the basic purpose of this is to perform encapsulation and decapsulation. I was showing that, right? A layer 2 frame comes, VXLAN encapsulated. That is your ingress VTEP. When the packet is going out, it is egress, right? That is egress VTEP. So here, same L2 network, right? It comes here. This L2 will get encapsulated on this VTEP, right? And this is your VXLAN header. I'm not showing UDP and all. You just like get encapsulated. This will traverse based on this IP address. So this is your ingress. When it reaches the egress, what it will do is it will rip off this, will take off this, and only L2 packet will go out, right? So the VTEP perform this encapsulation and decapsulation. Right? Let me clear this thing so that I can show you one more point, that each VTEP, as I was showing, right, it has two interfaces. One interface is towards the endpoint, which is your legacy, like same layer 2 interface, and the another one is towards the IP transport, right, where your encapsulated packet travel. So one side towards endpoint, this one. So this is your side number 1, and when the packet goes here, this is your side number 2. Right? Here it is encapsulated IP packets. Right? I hope this point is clear. Now let's move to the virtual network identifier. Right? What this VNI is. So let's take an example here. I have these two routers, let's say R1, this is R2, right? And those of you who understand VRF will relate to this. Let's say I have VRF1 here, VRF2 here, right? Same way, VRF1 here, VRF2 here, right? In between, I can have many nodes. Doesn't matter. They don't understand any of these things. VRFs are not created here. So now, tell me if there is a packet which comes from here for VRF1, right? This guy will know because this packet is hitting at an interface which is designated for VRF1. So R1 knows that, okay, this packet belongs to VRF1. It will send that packet to, let's say this is P1, this is P2. To P1, since there are no VRF here, P1 cannot identify this. Same goes with P2. And when P2 forward that packet, how R2 will know that this packet belongs to VRF1. Right? This is a famous MPLS scenario which is there running for ages. So what it do is VRF1, it actually allocate a label, let's say 10. And I'm highly simplifying this, that so this guy R2 has allocated a label 10 sent towards R1. So R1, while sending VRF1 packet, will put a label of 10 on this. So when the 10 reaches here, R2 will see that, okay, 10 I had allocated for VRF1. Same way, VRF2, it will allocate, let's say 20. It will send that here. So whenever R2 or R1 is sending a packet for VRF2, it will put that label of 20 onto it, so that the node on the other side can understand this, right? Very simple scenarios. So this 10, this 20 is your identifier. They are your virtual network identifier. In MPLS, in our this scenario, this is a 20-bit field. In VXLan, this is a 24-bit field. Apart from this, there is no difference. So a VNI is a value that can identify that virtual network in the data plane. How do you use it? What is layer 2 VNI, layer 3 VNI? For now, don't worry about it. We will cover those. But for this slide, the purpose of this is to convey what is a VNI. And hopefully you should be able to understand by now. So as I was saying, it is a 24-bit value. In MPLS 20-bit value, doesn't matter. Those are like enough value for us to identify multiple networks. Right? Now, we are shifting our gear from the VXLAN to actually the packet forwarding stuff. And to understand how this packet forwarding, this bridging, this switching works with EVPN, let's have a quick look at how it works in the traditional environment. And this is where I took the freedom of covering some thoughts provoking things as well. And it just happened that here in my current organization, there is a group of people who brainstorm on some, you can call it like silly questions. And then we go into those discussions and we just brainstorm. Right. So one occurrence of such discussion was like, why, or maybe I need to put it in the right way, do we need layer 2 network? Do we need MAC addresses when we have IP addresses? Is there a need that the EVPN fundamental purpose, as I told, right, that it help you to like extend your layer 2 domain, right? So do we really need to extend it? So for that, the next 7 to 8 minutes, let's go into the past a bit. And for those of you who are not interested to listen, can fast forward this. But the history of Ethernet, right? We are in 2023 as of now, and approximately 40 years ago, Ethernet started appearing, right? And the whole sole intent of this back in the days of TechNet, right? The organization, I think it was called as Tech, where they were working on inventing a protocol, is to have some mechanisms where devices on the same network or the devices which are connected via the same cable can talk to each other. So the idea was very simple, that let's say there is this cable and I'm connecting multiple devices via this, they should be able to talk to each other. If there are only two devices, technically you don't need any addresses because there is only one end, but they wanted multiple devices, right? So that's where they needed some address, and that's how the MAC addresses was allocated. And this protocol was actually LAT, local area transport, right? So this protocol, I'm covering a bit of history and then I will come into those thought-provoking sessions so that you are all on level with me. So the whole sole purpose of this LAT, right, was to forward the packet based on this same segment, right? It was never, now listen to me here very carefully, it was never designed to forward the packet across different Ethernet segments. And there was this another thing that was happening at that time, which was IP. And the purpose of IP was to communicate over different networks. But we will come back to IP later on. But now let's come back here. And as I was telling, when there are more devices, we needed some address. But soon, the demands that started coming from the users was that they needed a communication between two Ethernet segments. Now, the people who have invented LAT were in trouble because it was only designed for a single Ethernet segment. So, if you want to communicate from here to here, the simple answer is that we know today is you need a router, right? So, then the discussions that we were having in our room, right, in this closed room, is that why do we need MAC addresses in Ethernet frames? Why there are like the need of these two addresses? And again, this is a hypothetical brainstorming session, and I did find some evidence on the internet also. I will talk about those later on. But what we brainstormed is that why you need MAC addresses. It was somewhat up to a convincing logic, because in the same Ethernet segment, let's say this one, you have multiple devices, so you need some address. Okay, but now that IP had matured a lot, even IPv6 had matured a lot, do we still need MAC addresses? That was asked by one of the gentlemen. And we couldn't find any convincing logic, so we went with the most famous answer that I had even told you, like why there are so many reserved bits in VXLan, because of some backward compatibility. The same logic apply here also, that IEEE wanted to carry these MAC addresses along with it because it wanted some backward compatibility with these protocols that were invented at that time, right? But do I still need EVPN? Sorry, do I still need layer 2 network? I'm sorry, I'm taking EVPN because that's our topic, but do I still need layer 2 network? In many cases, you don't. And I will cover some of the advantages of layer 3 versus layer 2, and this is not a debate on that. I'm just sharing some thoughts around it. Feel free to put in the comments if you have some different thoughts. MAC address still exists, right? And by the way, why we are still using layer 2 addresses? One reason could be that every vendor think that they need to support this, because changing MAC address, changing that driver, changing that paradigm is a lot of work. Same way, you ask any service provider that, look, here is this emerging EVPN solution which support different route types, and out of those, one is route type 5. Do you still need VPN v4 into your network, sir, or you can just run with EVPN? They will say VPN v4 is running fine. I don't want to touch it. I will use EVPN to carry only the layer 2 network. Same way, vendor says MAC address is there, hardly encoded into the device drivers, and it's too much work for them to change it. So, and it's working, right? So why to disturb it? But if you will have any more thoughts around it, why we need layer two addresses, and don't come like, okay, MAC addresses are needed, IP addresses are needed because of one or other reasons, where you are doing switching based on the MAC address, a switch forward the packet based on the MAC address. All that is the result of all these things that we have done. Why a switch can only do a layer 2 lookup? Why can't a layer 3 lookup? Right? I'm just throwing some thoughts here. And why I'm like, we were discussing these things, right? Now there was no conclusion to this, but why we were discussing is because if you see the layer 3, right, they have some topological significance. You can summarize those, right? IP addresses are hierarchical, whereas MAC addresses are not. Why? I'm not involved into those discussions at that time. In fact, I was not even born at that time, but that's how it is. Right. So clearly, I'm talking about the advantages of layer 3 versus layer 2. Right. In layer 2, there is no hop count, there is no TTL. So if there is a loop in your layer 2 network, it will go forever. It is very difficult. You ask any network engineer. I had spent horrible nights in the NOC team troubleshooting such issues where there is a loop and the switch doesn't even allow you to log in. In IP, at least we have this TTL, right? But here in frames, there is nothing like that. And then layer 2 packets cannot be fragmented, whereas layer 3 we have that MTU value and it can be fragmented as well, if you are not I think setting that DF bit there. And then some of the error messages, right? ICMP unreachable or TTL expired, all these are not applicable to layer 2. But having said that, the point that I'm trying to say is that layer 3 is much more structured. But since we are carrying this legacy, right? And in fact, I will paste one link in the description by Radia Perlman, who was the inventor of STP. She says that layer 2 network doesn't make sense, but still we are utilizing it here. So whatever I have talked so far, uh, if you are unable to connect the dots with this, because this can itself be a big discussion altogether, I'm just covering it, as a glimpse of it. You watch that session and then you will be able to understand what I'm talking. So now let's come back to our discussion and erase this. And the layer 2 forwarding, right? We are talking about the traditional environments. So the layer 2 forwarding is, you can call the L2 forwarding as more of a guesswork, right? If you don't know where the destination is, send it to everybody. If you don't know where is Ravi sitting in the class, go ahead and shout, right? So that you can only guess that when I'm shouting, Ravi will hear. Or when I'm sending this broadcast in all the directions, the recipient, the intended recipient will hear it, right? So this is how this mechanism work with EVPN. Sorry, with in the traditional network, basically the flood and learn, and definitely this is not the efficient way. Whereas if I look at layer three, right, that is much more predictable. I would say much more deterministic. I would say, right. So, do you still need this layer two network? Go ahead and watch that session, which I will put the link into the description by Radia Perlman, and then maybe we can engage into the comments section for this video. Right. But for now, let's just see that we have this network where connected with leaf and spine topology. There is no EVPN for now. It is traditional, and all these links are layer 2 links, and I have, let's say, two VLANs, red and green, whose are connected. There are certain, ignore VNI for now. Actually VNI we will come later when we will change this scenario to EVPN. But for now, you just say that there are red VLAN and blue VLAN, green VLAN, and one of them have 10.1.1.0, another one 10.2.0. And for our discussion, we will be communicating from A to D. And for simplicity, I had kept this IP address 10.1.1.A, 10.1.1.D. So in the traditional network, when A just came online, D just came online, it is their first conversation. A doesn't know, because it is in the same segment, as it is clear from the IP address also, that they need the MAC address to communicate, and it doesn't know that. So what the A will do? A will follow the same strategy which Sunil had followed to find out who is Ravi in the class. So A will send that packet that will go in this direction, then it will come here, here, to everybody, right? That guesswork that I was talking. It will send it to everybody, and then finally here L3 we see that D is connected. A will send a unicast this time to A. Likewise, Ravi will stand up and come to me and say, "Hey Sunil, I am Ravi." That is unicast, right? And D will also follow the same strategy. Right? For now, those of you who are paying a very close attention to this network can clearly say that, Sunil, if we wear our networking hat for some time, come out of this beginner arena that you are understanding us, isn't it there is a loop? Let's say, let me use a different color here. Let's say that from L1, the packet goes to S1, right? Because this is broadcast. This will go in every direction. From S1, it will go to L2, right? Because L2 is directly connected. Now with L2, S2 is connected, and then S2 can send back to L1. That means there is a loop here. But this is where this wonderful lady that I was talking, Radia Perlman, invented STP. So STP was designed to avoid such scenarios where it will block those redundant links. Right? So this is how this flood and learn. Again, there are so many videos on YouTube. I just wanted to touch this context so that when we look at EVPN, basically you should be able to connect the dots. Right? So now let's just look at the EVPN part. Right? So the first thing first, as compared to the last slide, the link between the leaf and the spine, let's say here I have S1, here I have leaf, right? These links are routed links, layer 3 links. Remember VXLan forward packet on IP that we had seen, right? Leaf switches are act as a another fancy term, and V is, you can very well call it as VTEPs. Okay. So now let's just look at, in the same scenario, how does the EVPN forward the packets, right? Again, I have the host A and D. They want to communicate with each other. And I said, this side, it is still traditional. This side, it is VXLan. What does that mean? It is IP interfaces, right? So A, when it doesn't know D, it will again broadcast, right? It will again go and shout that where D is. The packet will come here. This guy will see that, okay, this is a broadcast packet. So what L1 will do is, L1 will also send it to everybody. Why everybody? Because remember, I told you that even though we have this encapsulation as VXLAN, even though we are using IP addresses for forwarding, even though it is layer 3, but still you are not allowed to change the fundamental behavior of Ethernet, which is flood and learn. Right? We will see how EVPN solve this, but that is the fundamental behavior of Ethernet. So what will happen here? That packet will come and then it will get encapsulated into IP, but this packet will be sent everywhere. When L2 will receive, L3 will receive, L3 will see that, okay, there is this red VLAN that is configured, or in this case it is VNI. Remember, when the packet comes from here, how L3 will figure out that this is part of red network, because here I will configure a value 100 for VNI. Same value I will configure here also, VNI 100, and I will put that value somewhere into this packet at 100. So when L3 sees that, okay, this is for 100, what does that 100 means? That means red Ethernet segment. So it will send that packet here, right? D will listen to this and D will say that, okay, this is my address, right? I'm talking about that ARP process. I hope you understand that. So D will respond to A, but before that, with EVPN, there is one more thing that will happen in this that doesn't happen with the traditional network. What that is? So when the packet comes here from A, be it a broadcast or whatever, right? It will have a source MAC address, a source IP address. What will be that? That will be the MAC and IP address of A, basically. So switch L1 knows that this MAC address of A and this IP address of A is connected on interface 1, let's say. Right. Now listen to me very carefully. What L1 will do, I am assuming that you have configured EVPN here, and we will see how to configure it in the upcoming session, but for now assume that you have configured EVPN here. L1 will send a BGP update to S1 and S2 that this MAC address is connected to VTEP L1 VNI 100. So what it will send, let's say MAC address is AAAA, I'm highly simplifying it, VNI is 100 and VTEP is L1. This entry will be sent via BGP to S1 and S2. Now S1 and S2 are acting as BGP route reflector. They will send this entry here towards L3. Right? So L3 will see that MAC address AAAA is connected behind VTEP L1 with VNI 100. So now when D, the packet comes from D, right, it will actually a ARP reply. Remember, we have already covered the flooding process. Now D had seen, and now D want to respond that, okay, here is my MAC address, basically. So D will respond with its MAC address. So what will be the source MAC here? Is of D, right? What will be the destination MAC here? That is of A, because D can extract that MAC address from the source MAC field, right? Here the source MAC was of A, the destination MAC was FFFF, right? That is how your ARP flooding works. If you don't understand, watch some videos. There are a lot of content. I don't want to go into the depth of that. My point here is to cover this in the context of EVPN basically. But here the destination is FFFF. The source is MAC A. When D respond, it actually reverses that. It says that, okay, I need to respond to A that this is my MAC address. So with the destination MAC address A, when the packet comes to L3, by now L3 already know that the MAC address is AAAA. It is connected behind VTEP L1 with VNI 100. So it will simply send that packet here. Right? Again, what will happen here? Now this L3, when this packet comes to L3, this packet, L3 will see that the source MAC address D is connected behind this interface. It will again send an update to BGP that MAC address D is connected to VNI 100 VTEP L3. BGP will send that information again to everybody. So now L1 knows that D is behind L3. L3 knows that A is behind L1. So BGP is basically distributing this information in the EVPN domain, in this domain. Here, this side, it is still traditional, flood and learn. Okay. I hope this is clear. Uh, but now we have talked about this, right? So D reaching out to A. If this concept is still not clear, let's just understand this via some animation, right? So for now, for the next slide, let me clear this thing here. You remember there is this L1 where A is connected, L3 where D is connected, and S1. So for the next animation, remember these three devices, L3, L3 to S1, S1 to L1, and then A, right, from D. So we are talking from the response from D to A. It will pass via L3, then S1, and then L1. Okay. I'm assuming that due to some load balancing, it chooses the path via S1, not via S2. So just for our demonstration, I'm not showing S2 here. So this is the payload, right? And then this is the source MAC. This is destination MAC, right? This is the packet which comes from D. Then it comes to the L3 device here, right? So what L3 will do? Because L3, the packet came from down, L3 has to send it towards S1. But S1, it's a VXLan network, IP network, BGP EVPN, right? So it will put some encapsulation. What is that first thing it will put? It will put that VNI ID. So that when the other side, the L1 receive, it knows that which VNI I need to put this packet into, right? After VNI, it will say that from that BGP update, remember I showed you that there was this BGP update which says that A is behind. So A basically, the MAC address of A is, let's say A, it's behind VTEP. Let's say, let's take that VTEP as L1, address of that VTEP as L1 and VNI 100. So VNI 100, or rather than calling it 100, let's call it as red VNI, right? So this red VNI, it has already put. The source address is VTEP L3 itself. The destination will be VTEP L1. From where this VTEP L1 came? From this update. BGP told it that it is behind L1. Right? Then it will, so now it need to forward the packet. To forward the packet, it need that MAC addresses as well, right? So it will put its MAC address, which is L3's MAC, and then S1 MAC. If I show you this picture again here, when the packet goes in this path, right, L3 MAC and S1 MAC, right? That's how your packet forwarding happens into the devices, right? So the packet is on this path now. Let's just build that animation again, right? So MAC S1. Now the packet comes to S1. S1 will see that, okay, it is my MAC address, so it open it up. Once it open it up, it will see that it is red VNI. This is the source VTEP, but the destination VTEP is L1. So what it will do is, we go back a bit. S1 will send this packet on this segment towards L1. Right? So it will put the MAC address of S1 as a source MAC, but the destination will be of L1. Right? So now when the packet reaches L1, L1 will decapsulate it and put it into the red VNI, because of this field, right? And this is how the packet get forwarded towards the A, right? So this is how this packet forwarding, this encapsulation of VXLan, all this that you see here, right, in this different color is VXLan encapsulation. So with that, we are already like into 70 minutes into this session. So let's end this. Just one request before we sign off from this video. If you see that this is something informative, you have learned something from this, please do share it in your network so that someone really can understand this emerging technology, right? And it can help them to enhance their skill set. So with that, I would like to say thanks a lot for your time and hope this was a valuable spent of your time. Thank you.